In this screencast, we're going to look at the fundamental theorem of line integrals, or the easy way to find work. The idea, work, is the integral of a force times a displacement. And we do an integral. Well, the fundamental theorem of line integrals says if the vector field has a potential, in other words, if you can find a little function f so that its gradient is the vector field, then the following works. Then all you have to do is find the potential and evaluate it at the endpoints and subtract. So essentially, if you're going along some curve and you want to find the work done from the beginning to the end, then all you have to do is find the potential and evaluate the function, the potential at the endpoint, and then subtract what happens if you evaluate it at the beginning point. The idea, well, first we'll just look at an example. Suppose your vector field is x plus 2y, 2x minus 4y. Does this vector field have a potential? Well, this is fx, that's fy, so if I calculate fxy and I calculate fyx, I ought to get the same thing. F sub xy is 2, and f sub yx would be 2. Those are the same, so a potential exists. I integrate this term with respect to x, giving me an x squared over 2 plus 2xy. I integrate this term with respect to y, giving me a 2xy minus 4y squared over 2. Then I add up terms, ignoring the duplicates, so the potential is x squared over 2 plus 2xy minus 4y squared over 2. If my curve is a curve which begins at the point 3, 0 and ends at the point 0, 2, then if I want to find the work from 3, 0 to 0, 2 of this vector field, x plus 2y, I'm going to write it in the form m dx plus n dy. That's probably a form you'll see often. Then in order to do this, all I really need to do is find the anti-differentiate. In other words, find the potential, x squared over 2 plus 2xy minus 4y squared over 2, and then plug in the endpoints. So first I put in the 0, 2, giving me 4 plus 0 minus 0. That's what happens when I put the 0, 2 in, and now I need to put the 3, oh, hold on, 0, 2, that'll make that a 0, that's a 0, and then that's minus 4 times 4, that's minus 8, sorry. So we get a minus 8, minus, now I put in 3, 0, and I get 9 halves plus 0 plus 0. So that is minus 8 minus 9 halves, and that's our answer. Why in the world does this theorem work? The idea is essentially akin to the fundamental theorem of calculus, where if you want to find an antiderivative of a function, and then you plug in the endpoints. I'm hoping that looks familiar. This theorem is essentially, if you want to calculate, you've got a derivative and you want to find a change. So right here I've got f of a, I'll call that a, I'll call that b, and that's f of b, and you want to find the distance between those. One way to do it is to chop it up into a bunch of little bits and find a little change in the distance. I'll call that df. Well, a little change in the distance, if you add up all the little changes, you get the total change, f of b minus f of a. If you want to actually do this, then we need to insert a variable. So I'm going to divide by dx and multiply by dx, and that's integrating f prime dx. That's essentially a proof of the fundamental theorem of calculus. How does it work in higher dimensions? Well, you take this exact same idea, the integral of df. The integral of df, if I'm going to insert a dt because I'm going along a curve, then this now becomes the integral from little a to little b of f prime of t. But f, notice our function f, here's our function f right here, it has no t's in it. So really you're taking a derivative with respect to t of a function, but you've got to evaluate it at points on a curve. That means that's a composition of functions. If you recall the chain rule said we integrate this thing by taking the derivative of f and multiplying it by the derivative of r. But the derivative of f is precisely the gradient, and the derivative of r is precisely r prime. And so if the gradient equals our vector field, then this becomes f dot dr. Here's our dr, here's our vector field, and that is now work. And so work is the same thing as taking the function and evaluating at its two endpoints. That completes the script.